moving from left to right on the x-axis with initial momentum P0 x, which is equal to Planck's constant divided by the initial wavelength lambdanot. Its momentum is represented by this arrow here. And this particle encounters a slit, a single slit in the Franhofer sense. And we're assuming the slit is within a screen. There's the slit here. We're assuming the slit is within a screen that has infinite mass, and the screen represents a potential barrier that is also infinite for the screen. The slit is actually an aperture of width A. So here's the particle moving from left to right towards this aperture, single slit diffraction. Since the particle is not confined in this region as it moves left to right towards the slit, you can think of it as planar wavefronts moving towards the slit from left to right. However, the difference in this example to normal examples you've probably seen is that in this example, the wavelength is more than twice the width of the aperture. So lambdanot is greater than twice the width of the aperture. Lambdanot is greater than 2A. Let's check and see that in the camera. Oh yeah. Okay. Lambdanot is greater than 2A. So this aperture is actually a sub wavelength aperture. Okay. Once the particle encounters the slit, there'll be a diffraction phenomenon. There's an uncertainty in its momentum in the y-axis. We'll get this the uncertainty in the y-axis momentum after the slit is given by deltaPy, which is the uncertainty in P, or momentum in the y direction, will be represented by an arrow pointing up or down. We'll just use up, imagining that the particle diffracted upwards after going through the slit. Now, normally, this uncertainty right here would be just given by h bar divided by the width of the aperture. So h bar divided by actually 2a, divided by 2 times the width of the aperture, and that would give your uncertainty due to diffracting through this slit, which confines the particle in the y-axis. So there's going to be an uncertainty in momentum in the y-axis, which creates the diffraction phenomenon. And that uncertainty is given by this, which is actually the standard deviation of the uncertainty in your y-axis momentum, is Planck's constant divided by 2a. That's all familiar. However, in the example, the original momentum, represented by P Pxnot equals h, just Planck's constant, not h bar, just regular h, Planck's constant, divided by lambdanot, the initial wavelength of this particle moving left to right. It could be an electron, it could be a photon. However, in this example, the uncertainty is actually greater than the available momentum in the first place. And since there's no other energy in the problem, and the conservation of energy restricts the amount of momentum available, the length of this vector can only be rotated up or down. So even though the uncertainty in the kind of normal non-sub wavelength aperture sense should be this standard uncertainty principle value, it actually has been restricted by the energy principle so that the vertical deflection in momentum that arrow can only be as long as this arrow here. So the most uncertainty you can have, the uncertainty is limited by the energy, so the most you can have is that arrow pointing down or that arrow pointing up. So in that case, the sub wavelength aperture, we'll just say that sort of the maximum uncertainty right here, which I'm going to call deltaPy restricted, has to be less than the initial momentum because of the energy conservation principle here. Now this only applies to sub wavelength apertures. So you wouldn't need this in a kind of standard diffraction problem, like if you have a laser shining through an NaCl crystal or something like that. That would be okay, as long as the laser's wavelength is significantly smaller than the spacing of the crystal. So the uncertainty of momentum in the y direction due to the aperture is less than the initial momentum by the energy conservation principle. Call that Pxnot equals h over lambdanot. So what you have when you combine these two equations is that, not only does h bar over 2a is actually less than h over lambdanot, or actually no, that's greater, sorry. H bar over 2a is greater than lambdanot. This is deltaPy y non-sub wavelength, non-sub lambda. But the case that we actually have to deal with here is this. So there's still an uncertainty, there's still a deflection, but the uncertainty has been restricted, so the maximum vector you can have is just this one tilted. So you have deltaPy restricted is less than or equal to the original momentum h over lambdanot. So this is kind of the correct equation to use for a sub-wavelength aperture. Incidentally, in this case, you notice that if this arrow is tilted upwards, if this arrow right here, if all of the momentum and all of its energy, momentum squared divided by 2 times the mass, if all this energy is deflected up or down, it basically means the particle is just traveling along the screen. It just goes this way forever. So, as far as where it would end up on a detector screen over here, it would never even get to the detector screen if you use this part of the equation equal to, because in that case, the arrow has been deflected, it goes upwards, so the particle never makes it to the detector screen over here. It just goes up forever or down forever. So, more lectures to come with Fourier transforms and the whole Gaussian distribution, which is cut off at the ends and whatnot. Thank you.